Okay, let's look at one more application from 6.4. So far, every time we've done a work problem, the force, so it's always sort of integrating a force function times distance, which is dx. So far, this force function has always come from working against gravity, right? From lifting things up or hauling chains up a cliff or something like that. So there's one other possible source of force that we're going to look at, which is an old physics classic called Hooke's law, where the force comes from a spring. So the idea over here is this block is on a frictionless surface, so there's no friction involved. It's just the spring. So it's just the stretching of the spring that makes you do work, right? And the thing that's important to point out about Hooke's law, I guess, is that the sort of natural length when the spring is just at rest is considered the starting point, or zero. That's where you're doing no work. Everything's just sitting there. And then when you stretch the spring and you move your object out here somewhere, that's what becomes x, is the amount of stretch. So the amount of stretch. And Hooke's law just says that the force is proportional to the amount of stretch. So really, when we do Hooke's law integrals, we're just going to have a kx dx. Our first task is always going to be to figure out this value for k. Excuse me. Figure out this value for k, and then we can do the rest of it. So let's just say, let's get at a little example here. Suppose it takes 20 pounds of force to stretch a spring. Let's see, a natural 8-inch spring. To 12 inches. So what is the work done? So this is kind of set up. This will allow us to figure out the k, basically. But then the actual question comes here. What is the work done in stretching from, let's say, like 15 inches to 18 inches. There's a lot of things in life, cables and whatnot, that actually act as springs, even though they're not an actual spring. So this applies to a lot of like bridge building and structural engineering. But anyway, so the first thing we need to do is figure out our little force equation, figure out actual Hooke's law here. So we know it takes 20 pounds of force. So Hooke's law says force is proportional to the amount of stretch. So it takes 20 pounds of force, and that's proportional to the amount of stretch. So we stretched it from 8 inches to 12 inches. So that was 4 inches. You know when we do pounds that we want feet, though. So this is 4/12 of a foot. 4/12, which is 1/3. So solve this for k, multiply both sides by 3, and you'll get k is 60. So the Hooke's law force for this particular spring is 60x. So now we can actually answer the question, when what is the work done in stretching from 15 inches to 18 inches? So work is integrating force times distance. And keep in mind again, this 15 inches to 18 inches, we need to talk about amount of stretch. And we also need to put it in feet. So 15 inches is 7 inches beyond natural length. So it's 7 inches of stretch. Or 7/12 of a foot of stretch. And 18 inches is 10 inches of stretch. So 10/12 of a foot of stretch. And I am not even going to finish that integral out. It's pretty easy to do this integral. The integration is very easy. So that's the basic setup of Hooke's law problems. They will give you some problems in the homework where instead of giving you all the setup here on the left-hand side of the integral, instead of essentially giving you all this stuff, they will occasionally actually give you the amount of work. Right? They'll tell you what the integral is equal to, and they'll say this came out, to 200 foot-pounds, or it came out to 60 joules if you're in metric or whatever. But they'll tell you that amount, and then they'll either give you both limits, and you essentially need to figure out what the K would have been, or they might give you the information to figure out the K in the problem, and you have to figure out one of the limits. That's the other possibility. So it might be that they're going to say from natural length, like how far do you stretch it, and you'll know the K, so you'll have something like 12.2x. How far will you have to stretch it before you do 200 foot-pounds of work? And again, you can work out the integral and just sort of plug in this unknown upper limit, set it equal to 200, and you'll be able to solve from there. All right, you have done a lot of work in this section. You are ready to handle questions 7 and 9 and 11. And then we'll finally move on to section 6.5. All right, good job. Good work.